So we're going to continue with our unit on covalent bonding and talk about bonding in homonuclear diatomic molecules. So these are molecules composed of two identical atoms. And so we're going to relate the molecular orbital model to these types of molecules. So for the lithium molecule, Li2, each lithium has an electron configuration of 1s2, 2s1. And so can we use both the 1s and the 2s orbitals to form a molecule? And the answer is no. The 1s are too small and they won't overlap, so we cannot use them. Now previously we had talked about examples that only involved valence electrons in the 1s orbital, so that was okay. But now that we're extending to 2s and eventually 2p, 1s aren't valence electrons anymore, and so they can't be used. So to participate in molecular orbitals, atomic orbitals must overlap in space. And so really we can only use the valence orbitals of the atoms to contribute significantly to molecular orbitals. Okay, well, the electron configuration for Li2, if we look at it in molecular orbital format, is sigma 2s2. Okay, because if you remember the, let's get a pen here, the electron configuration for lithium is 1s2, 2s1, and so each lithium is contributing one valence electron from the 2s, and so both of them together make two valence electrons, so that's where that 2 is coming from. So if we did the molecular orbital model, because we have two valence electrons total, those are going to go into the bonding orbital, and so if we do bond order, we have bonding electrons minus anti-bonding electrons, we don't have any, divided by 2, which is 1. That's a pretty high bond order, so Li2 is stable, but it doesn't mean that this is the most stable rearrangement. Lithium forms a solid as a molecule with several lithium atoms, so more than 2, and that is the most stable arrangement. Okay, let's look at beryllium. So if we look at Be2, there are bonding and anti-bonding orbitals in this model. Okay, here we go. So our beryllium electron configuration is 1s2, 2s2. And so if we look at 2 of those, we've got 2 valence electrons from each, and so it's a total of 4. So if we look at bond order, we have 2 electrons going in for bonded electrons and 2 going in as anti-bonded electrons, and we divide that by 2 and we get a bond order of 0. And so what this means is that the molecule will not form. It's not the most stable arrangement. Okay, so now we go to boron. Its electron configuration is 1s2, 2s2, 2p1. So now we have got p orbitals as well. And so to describe the molecule B2, we need to consider how many p atomic orbitals combine in order to form molecular orbitals. So when 2 borons approach each other, 2 pairs of p orbitals will overlap in a parallel fashion, and 1 will overlap head-on. And so this head-on is the sigma bonding and anti-bonding, and the parallel are also bonding and anti-bonding, but since they're above and below, we call those pi molecular orbitals. So if you remember from the hybridization, we had a sigma bond in the center between 2 atoms, and then if we had pi bonds, they were either on top or underneath, and so you can kind of think about it that way. So in order to relate this to molecular orbitals, we have pi 2p for the bonding orbitals and pi 2p asterisk for the anti-bonding. So let's look at some energies of sigma and pi. Sigma has a lower energy since the electrons are closest to the 2 nuclei because it's directly in the center of them. So remember, low energy is what we want. So sigma interactions are going to be stronger. So for the molecular orbital, 2s and 2p orbitals will combine separately. And so because each boron contributes 3 valence electrons. If you remember, each electron configuration was 1s2, 2s2, 2p1. So we've got 2 plus 1, so 3 valence electrons from each boron. And so that's 6 total. So if we do the molecular orbital model, we're going to put 2 into the bonding sigma, 2 into the anti-bonding sigma, and then 2 into the bonding pi. And so we've got 4 bonded electrons, 2 anti-bonding electrons over 2, which is 1, and that means that B2 is going to be a stable molecule. So here's a picture. Remember we said S and P are separate, okay, and so here's our boron atoms on their own, This is the 2s2, and here is the 2p1. Okay, we put 2 electrons into our bonding sigma, 2 into our anti-bonding sigma, and then 2 go into the pi. And remember, we're not doubling those up until they're all, until we fill one in each, and then we would go and double up. Okay, so most materials have no magnetism until they're placed in a magnetic field. But paramagnetism is when the substance is attracted into the inducing magnetic field. And we can also have dimagnetism, which is when the substance is repelled. We can measure this by taking the weight before and after an electromagnet is turned on, and if there's an increase in weight, that indicates that the sample is paramagnetic or attracted to the magnetic field. Paramagnetism is associated with unpaired electrons, and dimagnetism is associated with molecules that have all paired electrons. So a substance with paired and unpaired electrons is going to be paramagnetic, because paramagnetism is much stronger than dimagnetism, and so it will take over. So if we look at the molecular orbital energy level diagram for boron, it shows all paired electrons, which means dimagnetic, but it really is paramagnetic. And so the reason for this is because the assumptions with the molecular orbital model are that s and p orbitals combine separately, like we just talked about. But in reality, if they mix, boron, the molecule B2, ends up being paramagnetic. And so we can apply that same assumption to other period 2 elements. So if we want to kind of order the energy for molecular orbital diagrams, we can have sigma 2s, which is lowest in energy, and then we go to sigma asterisk 2s, and I'll just list them for you. And then we have pi 2p, and then, let's see, sigma 2p, and then pi 2p asterisk, and then sigma 2p asterisk. And so the energy increases as you go up that direction. So this is the order that molecular orbitals will fill. Probably going to be a good idea to somehow, I don't want to say memorize, but understand this order, because that way when you fill, you're going to fill in the right order. Okay, so a couple significant points. Correlations do exist between bond order, bond energy, and bond length. As the bond order increases, bond energy increases, and bond length will decrease. Bond order can't automatically be associated with a particular bond energy, though. Remember, we're saying there's a correlation, not a direct relationship. So both the boron molecule and the fluorine molecule have bond orders of 1, but the boron bond is twice as strong. Okay, so it's not giving you like a direct number, it's just giving you a relationship. Nitrogen has a bond order of 3, and that's due to the fact that it has a triple bond, and so it has a very high bond energy. And this strong bond is why many nitrogen-containing compounds are used as high explosives, because when you break that bond, a lot of energy is being released. Oxygen is paramagnetic, and the molecular orbital model predicts this, but if we look at the localized electron model, it would predict dimagnetic. Okay, so here's a picture of what's going on. The liquid oxygen will remain between the magnets until it boils away. And so it's pretty cool that it's attracted to these magnets, and it's just kind of hanging there in space. And so here's the link, and I've already got it set up, so let's go there. And I'll get out of the way.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled dewar. Then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet, and then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
So basically what they're doing is they're taking the oxygen and they're liquefying it, and they've already got the liquid nitrogen in, so this way they can pour both of them between the magnets and see, improve the oxygen as paramagnetic, and we'll find out what nitrogen is. And so here you can see they've got the liquid oxygen. Okay, so nitrogen first. So you can see it's nothing's really happening, it's just pouring through. Okay, so now the oxygen. So it's pretty cool. It's staying between those magnets because of its paramagnetism. Kind of a strong magnet. Okay. Okay, so let's look at a couple examples. So for each species, we want to give the electron configuration, bond order, and magnetism. So these are the three that we're going to look at. So let's look at F2- first. So if we look, let's get a pen. Okay, so each fluorine donates 7 valence electrons plus this negative, so that's 15 valence electrons total. Okay, so we want to give electron configuration, bond order, and magnetism. So if we look at the electron configuration, we want to put it in the molecular orbital electron configuration. And so we have, let's look at each fluorine first. We have 1s2, 2s2, 2p5. And so remember, 1s isn't part of this. And so we've got sigma 2s squared, sigma 2s asterisk, well, it's not squared, but 2. Okay, and then we've got pi 2p 4, and then sigma 2p 2, and then pi 2p asterisk, and sigma 2p asterisk, oops, and I forgot, not 2, okay, 4, and 1. Okay, so we've got 2 in the 2s, so 1, 2, 3, 4, 4 in each p, so that's 8, 9, 10, 11, 12, 13, 14, 15. And I went in order from lowest energy to highest energy. And so now let's look at bond order. So we need to look at bonding electrons and anti-bonding electrons. These are bonding, these are anti-bonding, these are bonding, these are bonding, these are anti-bonding, and these are antibonding. So now if we add up all the bonding electrons, we have 2 plus 4, so we have 6, 7, 8. So it's 8 minus antibonding, 1, 2, 3, 4, 5, 6, 7 over 2, and so that gives us 0.5. So this molecule will occur, but not a whole lot. Okay, we want to look at magnetism. We do have one lone electron, and so I would say that this is paramagnetic. Okay, let's look at the sulfur molecule. So again, we need valence electrons first. Each sulfur donates 6 plus another 2, so this is 16 valence electrons. So let's see, we'll go right here. So same order. And so I'm basically just going to fill, and then as each one gets filled, I go on to the next one in that order. Asterisk 4. Now here I have sigma 2p asterisk, and I have 2 of them. And so again, bonding and antibonding. So on my bonding electrons, I have 1, 2, 4, 6, 7, 8. So that's still going to remain 8 minus, okay, my antibonding. So I have 2. Oh, I probably shouldn't do stars. There's too many asterisks. It gets mixed up. 1, 2, 3, 4, 5, 6, 7, 8 over 2. So that's 0, which means that S2, 2 minus, is not going to be a molecule that will occur. And because we don't have any unpaired electrons, this is dimagnetic. Okay, let's look at our last one, which is Cl2, 2 plus. Chlorine contributes 7, so that's 14 minus 2 because of the 2 plus, so this gives us 12 valence electrons. And so we're going to start at sigma 2s, and then sigma 2s antibonding, and then we're going to go to 2p pi. So let's see, we want to go 12, so that's 8 so far, and then sigma 2p2, and then pi 2p antibonding. Let's see where we're at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and there's just 2 there. And so if we do all our bonding electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, minus our antibonding, 1, 2, 3, 4, over 2, so that's 4 over 2, which gives us 2. This means that this molecule is very likely to occur, and if we look at if there are paired or unpaired, for Cl2, because we have 2 electrons in the pi, remember we're going to fill each one before we double, and so that means we have 2 unpaired electrons, which means paramagnetic. Okay, so what I would like you guys to do is do the same for these two, and then we will go over them in class and make sure everybody's on the right track.